Let's finish up the Chapter 17 practice problems. For number 10, we have two charges. One of them is positive and one of them is negative. And we want to know which way does the electric field point at this location over here. So we did a similar one in class, where we just have to draw the direction of the field at each point due to each charge individually. So due to number 1 here, because it's positive, the electric field always points away from a positive charge. So that means that since it's going away in this direction, by the time you get to this point, it's still away in that direction. You can draw a straight line from the point to the charge, and that electric field must point along that line but away from the charge. And then over here we have a negative charge, so electric field always points toward a negative charge. So again, you can draw a dotted line here between the point and the charge and show that the field at that point is pointing towards that charge. So this over here would be E1 and this over here would be E2. So the net effect of these two fields, the y components will cancel out because the charges are the same and we're at the same distance in the y direction here. So the net effect will be a field this way because each of these two fields have an x component to the right that will add up to create a bigger x component. So the answer is vector EA. For number 11, a charge of 2 coulombs is at the origin when charge Q is placed at 2 meters along the positive x-axis. The electric field at 2 meters along the negative x-axis is 0. So we're saying right here, the field is 0. What's the value of Q? So this one is worded slightly differently, but it's the same concept that we've been doing. If we're trying to find the field here, in this case we're given the field here, but pretend we're trying to find the field here, well, you'd have to find the field due to each charge. So because this charge is positive, that means that the field due to this charge here must be going away from that charge. So again, I'll call this charge 1 and this charge 2. So this would be E1, the field due to charge 1. So the only way for the field here to be 0 is if the field due to charge 2 points in the opposite direction, so that these two fields, 1 and 2, could possibly cancel out and produce 0 field here. So if the field must point to the right toward charge number 2, that already tells us that this charge must be negative. That's why all of the answer choices have a negative charge. So how do we figure out what is that charge? Well, if the two fields cancel out to equal 0, then that means that E1 must equal E2 as far as the magnitudes of the fields. And that's given by KQ1 over R1 squared, that's the electric field due to charge 1, is equal to electric field due to charge 2. Again, I'm just looking at the magnitude of the field, not the direction, because we know the directions are opposite, which is why they cancel. So if we set these two equal to each other, then Coulomb's constant cancels out. And we just need to define our R values. So from the point to charge 1, that would be R1. That would be the 2 meters here. And from the point to charge 2 is 4 meters. R is always a distance from the charge to that point when you're talking about electric field. So now we just need to plug in these values. So Q1 was given as 2. R1 is 2, but we're going to square it. Q2 is what we're looking for, which is called Q here. And R2 is 4. We're going to square that. So we have 2 over 4 equals Q2 over 16. So you can cross multiply. 4 times Q2 equals 2 times 16. Sorry, this was not a square, this was a Q2 here. So 4 times what equals 32? 4 times 8. So Q2 must be equal to negative 8. We already discussed that the charge had to be negative, since the E field must be pointing toward that charge. But the magnitude of the charge is 8 coulombs, which is why the field can cancel. This charge is bigger than this one, but it is also further away. So in order to have the same impact as charge number 1, since it's further away at this point, it must have a bigger magnitude. Number 12. So this one is a plug and chug. We have a charge. And now again, this is kind of funny here. It's when it says a charge value, it's talking about the magnitude of the charge, because we know that an electron has a negative charge. So we have the field, what force. So again, it should be asking what magnitude force, what's the amount of the force that this charge experiences. So it really doesn't matter if it's an electron or a proton, because they both have the same charge. So Q prime is 1.6 times 10 to the negative 19 coulombs. So it would have been better if this problem just said an electron is moving, because you already know the charge of an electron. If you want to put a negative, that's fine, because it is a negative charge, but let's just assume that this is saying that there's an extra word in here that says magnitude force. So the field is 400 newtons per coulomb. So just to visualize, let's say the field is going this way. Well, that electron is going to experience a force this way, opposite the direction of the electric field. And the force is given by EQ. And that just comes from the definition of the electric field, which is the force per charge. Right, electric field is force per charge. So just multiply these two numbers together, and you will get negative 6.4. But this problem just asking for the magnitude, so that's the amount of force that a charge, either an electron or proton, experiences when placed in this electric field. And number 13 here, it says a proton initially moves left to right along the x-axis. It moves into an electric field which points in the negative x direction, travels a certain distance before coming to rest. So this is similar to the one we did in class, but it's asking for a different variable. First thing we want to do is visualize this. It says the electric field points in a negative x direction. So if the electric field points this way, then I like to visualize this as a positive plate and this is a negative plate, because the electric field between those two plates would point to the left. And then it says that the proton is initially moving to the right. But we know that it wants to move to the left. So if it's initially moving to the right, we know that it's eventually going to slow down, stop, and turn around, depending on how fast it was going to begin with. It's possible that it was going so fast that it'll slow down, but it'll still reach this plate. So in this instance, it travels a distance of 0.2 meters before coming to rest, so it does come to rest. So let's go ahead and write down our givens here. So it's traveling delta x right here, this way to the right. So delta x is 0.2 meters, and the initial speed or velocity is 2 times 10 to the 3. It comes to rest, so that means the final speed is 0. And we're looking for the acceleration. Well, in this case, this is really just a kinematic equation problem, because we are given 3 out of those 5 variables for the kinematic equations. So if we're looking for A, then use a kinematic equation that has all 4 variables. Vf squared equals V initial squared plus 2A delta x. And the Vf is 0, so Vf squared is 0. Solve for A, you'll get negative Vi squared over 2 delta x. Plug in these numbers here, and you will get a negative number, but it did ask for the magnitude here, so that's why the final answer is positive. So usually for this type of problem, this would just be one part of the problem where maybe you need acceleration, but then maybe once you know that acceleration, then you could find a force because you know the mass of the proton. You could do force equals ma, and then once you have that force, then maybe it would ask for what's the electric field. You could do electric field is force divided by charge. But this one just asked that first step of that problem.